Today, we're focusing on the Data Center MVAC System, Advanced Module 18. Our goal here is to ensure continuous cooling availability by following disciplined operations, predictive maintenance, and effective emergency response, all while managing controlled change. Key areas include CPOS and BMS integration, maintaining water quality, implementing preventive maintenance, managing spares, preparing for emergencies, and emphasizing training and audits. This advanced training is designed to enhance our readiness and ensure the system runs smoothly in all conditions. This module focuses on operations, maintenance, and readiness for data center MVAC systems. Our purpose here is to sustain thermal continuity by combining disciplined procedures, condition evidence, competent people, and controlled change. The goal is to protect life, IT load, and cooling availability while converting design intent into repeatable field behavior. Every intervention should be auditable and reversible. By the end of this training, you'll be able to build SOPs, MOPs, EOPs, and EMP content, select preventive maintenance, predictive maintenance, and corrective strategies, and verify residual capacity along with return-to-service conditions. This content is especially relevant for facility and duty managers, mechanical and controls engineers, commissioning engineers, as well as OEM, vendor, and maintenance teams. Our operating principle is to work strictly within the approved envelope, intervening only when you have the proper authority, capacity, and evidence. Proof of readiness involves a combination of people, procedures, plant state, tools, spares, and acceptance criteria. Keep in mind that while examples in this training are generic, actual work must always follow approved project data, OEM limits, and local authority requirements. This module focuses on operations, maintenance, and readiness for data center MVAC systems. The key starting point is using standards as a framework, but remember, the actual site must follow the approved design, OEM instructions, and local laws. The primary operating basis includes the approved owner's project requirements and basis of design documents, as-built drawings, OEM manuals and warranties, site risk assessments, authority having jurisdiction rules, and the current operating envelope. Our O&M framework draws on established procedures from BICSI 009, infrastructure context from TIA 942C, operational behaviors from Uptime TCOS, and performance KPIs from ISO/IEC standards. Lastly, keep in mind the addition control. The BICSI 009-2019 document is the baseline, but ANSI/BICSI 009-2024 is the latest version. So conducting a documented gap review before adopting the new standard is essential. This module focuses on the operations, maintenance, and readiness of the data center MVAC system, guiding us through a comprehensive learning route from intent to operating proof. We follow a repeatable chain, starting from the design basis and moving through safe restoration and lessons learned. Key steps include governing, documenting, monitoring, detecting, deciding, authorizing, isolating, maintaining, testing, restoring, verifying, recording, learning, improving, training, drilling, auditing, and assuring. Each step is crucial to ensuring system reliability and safety. Before any intervention, there is a readiness gate where approved basis, live load, alternate paths, competent personnel, and stop work limits are confirmed. This ensures controlled execution, progressing through declared plant states with hold points, independent checks, and a credible rollback path. Finally, operating proof must be demonstrated, showing capacity, safeties, controls, alarms, redundancy, and stable load response before closeout. Throughout this process, we rely on key procedures: SOP for standard operations, MOP for maintenance methods, EOP for emergencies, and MOC for managing changes. This module, titled Operations, Maintenance, and Readiness, is designed to give you comprehensive skills for managing MVAC systems in live data centers. By the end of this training, you will be able to plan, authorize, execute, and prove MVAC work with confidence. We'll focus first on engineering competence, where you'll learn to map thermal service paths and failure domains, quantify available duty and maintenance margins, and define acceptance limits before starting any work. Moving to operational competence, you'll develop the ability to select maintenance types based on risk, run controlled SOP, MOP, and EOP sequences, and verify that normal lineup and redundancy are restored. Throughout, we'll emphasize critical elements like controls, evidence, cooling plant operations, liquid cooling techniques, and emergency response. Understanding these areas will ensure your competency in managing MVAC systems safely and effectively. On this slide, we outline the detailed agenda for Module 18, which focuses on operations, maintenance, and readiness of the data center MVAC system. The training covers a practical workstream starting from governance and maintenance planning all the way through to emergency recovery and handover. First, we'll look at governance and records, including key aspects like roles, shift handover, document control, and how patrols, CMMS, change control, and risk review are managed. We'll also cover project-specific SLAs and escalation procedures to ensure accountability. Next, maintenance engineering is addressed, with topics such as preventive, predictive, and corrective maintenance, as well as situational work. We'll dive into EMP task design and release gates, along with managing spares, vendors, and special tools required for the system. For the MVAC asset programs, the focus will be on critical components like chillers, CRAH, FWU, DX units, pumps, and thermal energy storage, along with heat rejection, water, and airflow systems. Controls including CDU, DTC, and immersion systems are also part of this section. Finally, the emergency and readiness segment covers emergency operating procedures, command and thermal stabilization, drills, event record management, root cause analysis, and procedures for handover, competency verification, and audit readiness. Throughout the module, we'll refer to key procedures like SOP, MOP, EOP, and MOC to ensure everyone understands the standardized approaches we follow. This comprehensive agenda ensures a systematic approach to maintaining and operating the MVAC system efficiently and reliably. This slide covers the core aspects of MVAC operations governance, focusing on authority, risk, readiness, and evidence. We begin with the asset register and criticality, which is essential for understanding what equipment is vital for operations. Next, we rely on approved standard operating procedures, methods of procedure, and emergency operating procedures to ensure consistency and safety. Work authority and lockout-tagout procedures are critical controls to manage risk and maintain safety during maintenance or operation. We then perform risk and redundancy checks to ensure the system's resilience against potential failures. Execution and monitoring follow, allowing us to track work progress and system performance in real time. Functional proof verifies that the MVAC system operates as intended before restoring it to service, which must be signed off to confirm compliance. On the responsibility side, the owner defines the operating envelope, while maintenance and OEM verify it. Maintenance prepares the plan, and the operator approves it. In emergencies, the operator leads, supported by all parties, and returns the system to service only after independent evidence review. Speaking of evidence, a strong evidence chain is mandatory. It includes documented requirements, methods used, results obtained, acceptance criteria, and signed approvals. Importantly, no return to service is allowed until protections, controls, alarms, and redundancy are verified. Finally, the readiness pillars ensure we have a skilled team, necessary spares, calibrated instruments, up-to-date drawings, and conducted drills. These elements collectively guarantee that the MVAC system operates reliably and safely at all times. This slide outlines the crucial roles involved in the operations, maintenance, and readiness of a data center MVAC system. The operations organization revolves around one accountable owner who oversees many coordinated roles. Before any event occurs, it's essential to have clear local response plans, defined engineering authority, and vendor support. The data center manager holds accountability for service levels, resources, budgets, risk acceptance, and setting cross-functional priorities. Facilities operations are responsible for 24/7 monitoring, conducting rounds, managing alarms and permits, executing maintenance operations procedures, handling restorations, and maintaining shift logs. Engineering and controls own design authority, sequence of operations, set point changes, failure mode analysis, and technical escalation. Finally, OEM and service partners provide trained specialists, parts, remote support, and defined response times, all outlined in enforceable contracts. This collaboration ensures smooth and reliable data center operations. This slide covers the critical concept of system boundary and interface ownership within the data center MVAC system. Every interface must have a clearly defined owner, along with a live status signal, acceptance criteria, and restoration rules. Starting with the thermal service path, it flows from the IT demand through air or liquid terminals, then distribution, and finally to heat rejection. At every handoff point along this path, capacity must be declared and acceptance confirmed, making it clear who owns each isolation boundary. For controls and sensing, local safety remains the primary authority, but the Cooling Plant Optimization System, CPOS, coordinates approved operational modes. Commands, feedback, alarms, and overrides are all synchronized in time to ensure proper response. There are also shared dependencies critical to system operation, including power supplies with normal and standby modes, the controls network, makeup water systems, chemistry monitoring, leak detection, as well as systems for data logging, maintenance management, and current drawings. Understanding these ownership and interface rules is essential to maintain operational readiness and to ensure smooth coordination across all components of the MVAC system. This slide covers the controlled document hierarchy crucial for operations, maintenance, and readiness in data center MVAC systems. Operators must always know which document authorizes the task, defines the steps, and records the result. Starting with policy and design basis, documents like the owner's project requirements, basis of design, approved as-builts, and safety rules set the framework for what is allowed. Then we have execution documents, standard operating procedures, methods of procedure for planned work, emergency operating procedures for abnormal events, and recurring maintenance tasks outlined in EMPs. Finally, the evidence and learning phase includes work orders, permits, data trends, photos, sign-offs, change records, and event reports to ensure continuous improvement and accountability. This hierarchy ensures every task is clearly guided and documented from start to finish. On this slide, we're focusing on the operations-ready MVAC architecture, which is crucial for maintaining data center cooling systems efficiently and safely. First, we emphasize the need to protect redundancy by keeping alternate capacity available during both operations and maintenance. This ensures the system can continue functioning without interruption. Next, maintaining access is about providing safe service clearance and positive isolation, allowing maintenance teams to work securely. It's equally important to verify the physical response using calibrated instruments and documented records after any work is done to confirm the system's performance. The slide also highlights key components like IT racks, CRAH units, chilled water supply and return headers, pumps, chillers, cooling towers, and associated isolation valves. Water treatment elements such as expansion tanks, chemical dosing, side stream filters, and leak detection are essential for system longevity. Finally, the building management system plays a vital role by providing command, status, alarms, and time-aligned evidence to support ongoing monitoring and maintenance activities. Together, these principles and components create a robust framework for reliable and measurable data center cooling operations. This module focuses on operations, maintenance, and readiness of the data center MVAC system. Our main scope is to maintain the entire heat removal chain, ensuring every component performs reliably. We start by inspecting the asset thoroughly, looking at its service access, dependencies, and key evidence points that confirm it can return to operational duty. Equipment identification is critical, covering chillers, dry coolers or towers, heat exchangers, CRAH units, fan wall units, DX or VRF systems, pressurization fans, pumps, plate heat exchangers, thermal energy storage, coolant distribution units, and immersion loops. Maintenance access must be evaluated for correct isolation and lockout-tagout points, proper provisions for draining, venting, recovery, and lifting, as well as safe clearances and contamination controls. Finally, operating proof involves verifying the nameplate against approved submittals, checking command and feedback signals, safety mechanisms, alarms, and monitoring temperature, flow, pressure, vibration, and power parameters to ensure everything functions within the required specifications. In this module, we're focusing on the critical process of shift handover, which is essentially a controlled transfer of plant risk. The overlap duration between shifts is defined by the site, and it's crucial that the content and acceptance procedures are strictly followed to ensure a reliable handover. Now, key elements we need to cover include the plant state, such as duty and standby lineup, capacity margins, and the state of charge for the thermal energy storage or TES, as well as any degraded, isolated, or inhibited equipment. Active work must also be communicated clearly, including any open maintenance procedures, permits, vendor attendance, and the status of critical items like temporary hoses or bypasses. Alarms and overrides are another vital area, where incoming staff need to be aware of active or shelved alarms, manual commands, and any sensor or calibration issues. Finally, acceptance involves the incoming shift reading back all critical information, confirming dashboard and field conditions, signing the log, and escalating any uncertainties. This thorough approach helps maintain plant safety and operational continuity. In this module, we focus on operations, maintenance, and readiness of data center MVAC systems. Routine patrols play a crucial role by converting weak signals into early action, helping us catch potential issues before they escalate. These rounds are essential because they supplement automated systems like the building management system and the cooling plant optimization system. While those systems rely on sensors, patrols detect things sensors might miss, such as unusual odors, sounds, leaks, or physical conditions. During rounds, we carefully observe for noise, vibration, odor, heat, discoloration, leaks, stains, corrosion, debris, and any loose hardware. We also check access, housekeeping, and containment integrity to ensure everything is in good shape. It's important to record detailed information, like the date, time, route, asset involved, readings taken, photographs, comparisons to prior conditions, priority level, owner, and due date. If any changes could impact normal function, we escalate the issue by opening an ad hoc investigation and safeguarding redundancy before taking any equipment offline. Finally, every finding is tracked to verified completion in the maintenance system, and if a problem recurs, it may trigger a deeper equipment maintenance plan or design review. This systematic approach keeps data center systems reliable and ready to meet demand. Here we have a worked example focusing on asset availability and maintenance headroom for a data center MVAC system. Starting with asset availability, the mean time between failures is given as 8,760 hours, and the mean time to repair is 4 hours. Using these values, we calculate asset availability as the ratio of MTBF over the sum of MTBF and MTTR, resulting in a remarkable 954% availability. This translates to an expected unavailability of approximately 4 hours per year. Next, considering system maintenance headroom, the system consists of 3 chillers, each rated at 1 megawatt, giving a total installed capacity of 3 megawatts. The critical duty load is 2 megawatts, and if one chiller is isolated for maintenance, the available capacity is exactly 2 megawatts, which matches the critical load. That means at this load, the headroom is 0%. There's no extra capacity left for unforeseen demands or maintenance. To maintain a 20% headroom, the eligible load must be reduced to 1.6 megawatts, creating a reserve capacity of 0.4 megawatts. This reserve is essential for operational flexibility and reliability. Importantly, even though the calculated asset availability is very high, it doesn't guarantee system maintainability. Other factors like system topology, common failure modes, actual load conditions, control strategies, and restoration procedures are critical and must be managed carefully to ensure overall system resilience. This slide covers the operational design criteria and declared assumptions essential for maintaining and operating a data center MVAC system. First, it's critical to understand that maintenance cannot be authorized until key factors like load, environment, redundancy, and evidence boundaries are firmly established and frozen. This ensures stability and safety in operations. Looking at thermal duty, we must consider the current and forecasted IT and MVAC loads, along with the coincident peak, ramp rate, and diversity. Equally important are the required supply and return conditions, making sure design margins are carefully separated from standby capacity to optimize efficiency. Environmentally, we have to account for outdoor design constraints, contamination exposure, and the differences between recommended and allowable equipment limits, especially concerning dew point, condensation, and water constraints. Preparing for flood and seismic conditions also shapes the operating posture. Maintainability focuses on defining the smallest isolatable segment and ensuring there is sufficient residual capacity after isolation. It also involves considerations for shared power, controls, water, and network modes while providing clear access, drainage, recovery, and equipment lifting routes. Finally, the slide highlights several critical concepts such as the load basis, thermal envelope, failure domain, standby path, work window, and evidence plan, all necessary to support a reliable and robust MVAC system for data center operations. This module focuses on the controlled operating envelope of a data center MVAC system across normal, maintenance, and failure states. It's important to understand that a set point alone doesn't define this envelope. Instead, we need to specify the allowable range, the duration within those limits, alarm boundaries, and the recovery actions needed if those boundaries are crossed. The envelope registers key parameters like chilled water supply and return temperatures, room inlet temperature and relative humidity, flow, differential pressure, valve position, pump speed, chiller lift and heat rejection limits, as well as liquid cooling supply temperature and dew point margin. Each state has specific limits. During normal operation, the system runs efficiently and stably. In maintenance, redundancy is reduced and monitoring tightens. Failure states trigger survival limits and load shedding, and recovery involves a proof period before fully restoring normal operation. Understanding these states and their limits is crucial for maintaining system readiness and reliability. Here we have a worked example focusing on residual capacity before releasing a chiller for maintenance. The key message is that simply relying on the installed N+1 label isn't sufficient. Instead, we authorize work based on the live coincident load and credible contingencies. We start with 4 chillers, each rated at 1.50 megawatts of cooling. One chiller is isolated for maintenance, leaving us with an available capacity of 4.50 megawatts. The current measured load is 4.20 megawatts, with a forecasted additional load of 0.15 megawatts. Subtracting the load and forecast from the available capacity leaves us a residual margin of 0.15 megawatts, which is about 3.3% of the available duty. Next, we assess the next failure exposure. If another chiller trips, dropping capacity by 1.50 megawatts, the available duty would fall to 3.00 megawatts. This creates a significant deficit of 1.20 megawatts, so it's crucial to schedule maintenance during lower load periods or add mitigations. The decision to release the chiller hinges on a series of verification steps, including confirming standby path readiness, control checks, and having emergency operating procedures in place. We must have solid evidence such as time-aligned load trends, valve lineup verification, standby start tests, and rollback readiness. The final release is conditional, with a defined load ceiling, continuous monitoring, clear stop work triggers, and approved mitigation plans for the next credible failure. This approach ensures both system reliability and safe maintenance operations. This slide outlines the critical maintenance execution sequence for data center MVAC systems, focusing on 3 key principles: protect capacity, isolate safely, and prove restoration. We start by declaring the scope and approved method of procedure. Next, we check the load, weather conditions, and redundancy to ensure a safe operating envelope. Then we start and prove the standby equipment is stable before transferring the load and confirming temperatures remain steady. Once stable, we isolate the equipment using lockout, tagout, and draining procedures to verify zero energy. Maintenance or repairs are then performed, with workmanship carefully recorded. After that, static checks confirm valves and protections are set properly. A functional test under load compares command signals to physical response. Finally, we controlledly restore the system, close alarms, and sign off on evidence. Throughout this process, hold points are vital: accepting load capacity, proving physical isolation, passing functional tests, and ensuring alarms are cleared. It's important to stop work immediately if safe capacity, isolation, or restoration evidence is not confirmed. This structured approach ensures system reliability and safety from start to finish. Here, we focus on operations, maintenance, and readiness for the data center MVAC system. One key point is that maintenance risk peaks during transition. The moments when we move into and out of maintenance mode are often where human errors are most likely to happen, rather than during the maintenance task itself. Before isolation, it's critical to confirm several factors: ensuring the system is in a normal state, verifying the live load and alternate path, following the correct procedure, and making sure the team is competent and equipped with the right tools, spares, and communication channels. During maintenance, the alternate path must be protected. Simultaneous work in the same failure domain should be prohibited, and tighter monitoring of thermal and control limits is necessary. Finally, when returning to normal, all temporary states must be removed, safeties and load responses should be proven, overrides closed, standby restored, stability trends analyzed, and an independent sign-off obtained for full assurance. Understanding and following these steps reduces risk and ensures a smooth maintenance process. This slide focuses on selecting the right maintenance strategy based on failure behavior and the risks associated with intervention. A top-tier maintenance program blends different methods. It doesn't rely on putting every component on the same fixed schedule. We start with interval preventive maintenance, which is great for predictable wear and tasks required by warranties or authorities having jurisdiction. The key here is to base the interval on the original equipment manufacturer's guidelines and actual operating history. Next, condition-based or predictive maintenance uses measurable data like vibration analysis, thermography, fluid testing, differential pressure, temperature approaches, and electrical current signatures. This lets us spot issues before they cause failures by tracking trends over time. Finally, corrective or situational maintenance is about fixing things when they fail, which works well for non-critical, low-risk components. But for critical assets, it's crucial to have a rapid response plan, spares ready, clear authority for repairs, and proper restoration tests in place before any failure happens. Understanding these distinctions ensures that maintenance efforts are both efficient and effective, targeting the right components with the right strategies. This slide focuses on the Equipment Maintenance Plan, or EMP, which is the foundation behind every recurring maintenance task in our data center MVAC system. The EMP takes manufacturer guidance and site-specific risks and transforms them into actionable, budgeted, and traceable work orders. Starting with the asset header, we capture detailed information such as equipment type, tag, location, and the service path. We also include documentation and validated nameplate data, along with the criticality, failure domain, and redundancy roles of the equipment. Plus, environmental or duty class differences are noted to tailor the plan appropriately. Next, in the task definition, each task has a clear title and description, along with specific triggers based on a calendar, meter reading, or condition. We also define the running or shutdown conditions and assign a unique procedure or task identifier to ensure clarity and traceability. Finally, execution support outlines the practical requirements: the craft and number of personnel needed, estimated duration, and any planned outage hours, as well as necessary tools, PPE, consumables, and spare parts. Acceptance readings and closeout evidence ensure the task's successful completion and verification. This comprehensive model helps us maintain peak readiness and operational reliability. In this module, we focus on the CMMS work order lifecycle, which is crucial for effective operations, maintenance, and readiness of the data center MVAC system. A work order is considered complete only when the plant state and evidence are fully restored, not just when the physical work ends. It starts with the plan phase, where we identify the asset or task, set priorities, assess risks, and gather all necessary resources like procedures, materials, labor, vendors, and outage criteria. Next comes authorize, which includes approvals, permits, lockout/tagout procedures, capacity checks, notifying stakeholders, and conducting pre-job briefs. Then we have the execute phase, where all actions are time-stamped, actual readings and any deviations are recorded, parts used are logged, photographs are taken, alarms monitored, and peer verification is done. Finally, in the close and learn phase, we perform return-to-service tests, ensure normal lineup, monitor trends, get sign-offs, replenish spares, update history, and make EMP changes if needed. This thorough life cycle ensures reliability and accountability throughout the maintenance process. On this slide, we focus on the critical concept of the maintenance release gate for data center MVAC systems. No live data center work should begin until several stringent conditions are met. These include verifying residual capacity, ensuring proper isolation, confirming independent paths, and having credible restoration proof. First, capacity means the live load plus any forecasted load must remain below the available duty, with standby systems tested and proven to start and accept load reliably. Isolation involves identifying the smallest safe segment for work, controlling lockout-tagout, drains, vents, pressures, and stored energy to prevent hazards. Independence requires that alternate power sources, control systems, networks, headers, and chemical processes be beyond the scope of any failure caused by the ongoing work. Human factors are equally important, with a competent team, peer checking, clear labeling, up-to-date maintenance operating procedures, effective communication, and stop work authority firmly in place. The maintenance release gate outlines 6 essential steps: declaring the load, mapping the failure domain, proving the standby path, safely isolating the work area, testing under load, and finally restoring the system and signing off. A crucial hold point ensures no progress occurs if there's any doubt about safety, capacity, isolation, path integrity, drainage, sensing, or restoration evidence. This thorough process helps maintain data center reliability and safety during maintenance. This slide outlines the essential steps for preventive and predictive maintenance tasks in data center MVAC systems, emphasizing a structured and thorough approach. We start by risk ranking the work to identify priorities, then protect redundancy to ensure continuous operation. Next, we follow approved methods of procedure and lockout/tagout protocols to guarantee safety. Inspection and measurement come next, focusing on critical parameters to detect potential issues early. Repair or replacement is performed as needed, followed by functional testing under load to confirm system performance. Finally, we restore the equipment and record all activities comprehensively. Looking at specific equipment, for chillers we check tube cleanliness, oil and refrigerant samples, and interlocks, with proof including capacity and alarm verification. Pumps require alignment checks, seal and bearing conditions, vibration analysis, and proof through flow and pressure monitoring. Cooling towers involve basin and nozzle inspections, water quality, and fan status with approach temperature as validation. CRAH units and fan walls need filter and coil checks, bearing assessments, and airflow measurements. Plate heat exchangers call for coolant sampling, leak detection, and pressure monitoring, ensuring heat transfer efficiency. Valves, sensors, and meters are verified through actuator and calibration checks to match commands accurately. Water treatment involves monitoring chemical dosing, pH, and filtration effectiveness, with proof confirming clean surfaces and proper chemistry. Critical spares such as seal kits, actuators, VFD modules, sensors, filters, gaskets, and water quality probes must be readily available to avoid downtime. Before and after maintenance, key performance metrics like chiller approach temperature and pump vibration are compared against target ranges and alarm limits to validate success. Closeout includes approved work orders, calibrated test results, closed alarms, spares usage, failure codes, and signed return-to-service documents. Remember, maintenance is only complete when capacity, controls, protection, and redundancy are physically proven. This comprehensive process ensures reliability and readiness of critical data center cooling systems. This slide outlines the cooling preventive maintenance calendar for data center MVAC systems, which is part of our advanced training. Maintenance frequencies are just starting points here. OEM requirements, duty hours, condition trends, warranties, and local authority rules ultimately shape the final equipment maintenance plan. On a monthly basis, we monitor environment and set points, supply and return temperatures, differential pressure, leaks, filters, drains, valves, belts, alarm history, water makeup, and chemistry. Moving quarterly, leak checks are repeated, blower and motor hardware are verified. We record motor currents as well as reheat and humidifier currents, and review trend drift alongside nuisance alarms. Semi-annually, coils are inspected and cleaned, contactors, relays, and wiring are checked, regulating valves are stroked, and safeties and operating sequences are tested. Finally, annually or based on usage, infrared thermography is performed, vibration baselines established, bearing and coil tasks conducted according to hours and condition, calibration is completed, performance tests are run, and OEM overhaul scopes are addressed. This layered approach ensures we keep systems reliable and efficient over time. This module focuses on chiller maintenance and how it's essential to protect capacity, efficiency, and refrigerant integrity. Instead of relying on generic fixed replacement intervals, it's crucial to use OEM limits and trend baselines tailored to each specific model. Starting with the mechanical condition, key checks include compressor vibration, oil and bearing health, evaporator and condenser pressure drops, relief devices, and refrigerant leak inspections. Isolation procedures, purge and recovery processes, and readiness for lifting are also essential. On the electrical and controls side, monitoring the variable speed drive and power quality is important, along with inspecting starters, contactors, and relays. Sensor calibration and safety chain verification ensure safety, and always back up firmware and configurations before making any changes. For performance proof, tracking parameters like chilled water supply and return temperatures, flow rates, power consumption, and calculated cooling capacity helps monitor load behaviors and restart sequences. Comparing these results with a clean baseline and the OEM's performance map completes a thorough analysis. This comprehensive approach covers all critical components: compressor, heat exchangers, refrigerant system, drive, safeties, and overall performance to maintain optimal operation. This module covers the essential aspects of operations, maintenance, and readiness for data center MVAC systems, focusing on advanced training for CRAH, FWU, and DX maintenance. It's important to understand that terminal units aren't maintained as isolated fans, but as integrated systems, including airflow, heat transfer, drainage, valve, and control assemblies. Starting with the air path, we closely monitor filter differential pressure and condition, ensure coil cleanliness, and check for any fin damage. We also assess EC fan vibration and current to verify proper operation, along with the availability of the fan array. Containment, bypass, and return air paths must be checked to maintain efficient airflow. Next, the water and refrigerant path requires attention to the functioning of PICV and PICCV valves, including their stroke, feedback, and authority. We measure coil temperature and pressure differentials, as well as perform air venting to avoid trapped air. The condensate system, pan, trap, pump, and leak sensors are crucial to prevent water damage. Additionally, DX components like compressors, expansion valves, and leak integrity are regularly inspected. Controls and proof points include calibrating inlet and return sensors, comparing fan and valve commands against feedback signals, and monitoring alarms for loss of flow, dirty filters, and condensate issues. Finally, we conduct duty tests at representative rack loads to validate system performance under real conditions. The focus areas break down into filters, coils, fans, valves, drains, and controls, each critical to maintaining system reliability and efficiency. Remember, understanding these elements and their interdependencies ensures that the data center MVAC system remains operational and ready for any demand. This module focuses on the operations, maintenance, and readiness of data center MVAC systems, with a particular emphasis on pumps, hydronics, plate heat exchangers, and thermal energy storage. One key point to understand is that distribution integrity is essential. Without it, loss of flow, hidden corrosion, or a failed shared valve can compromise even redundant cooling equipment. When we talk about pumps and valves, it's crucial to monitor bearing and seal conditions, alignment and vibration, as well as suction and discharge pressures, flow rates, and electrical consumption. We also need to ensure the variable speed drives are properly cooled and configured, and check for any valve strokes or leakages. For piping and plate heat exchangers, inspecting for external corrosion, maintaining supports and insulation, and checking the interior condition are vital. We use tools like strainer differential pressure, air and dirt separation, and expansion control to maintain system health. For thermal energy storage readiness, verifying the tank's lining and leak condition, sensor accuracy, and temperature stratification is important. Proper sequencing of charge and discharge valves, alongside pump and control power assessments, completes the maintenance picture. This comprehensive approach helps maintain optimal system performance and reliability. This module focuses on operations, maintenance, and readiness for data center MVAC systems, specifically the heat rejection components like dry coolers, condensers, and cooling towers. Maintaining the thermal sink and its water quality is crucial, as shared dependencies can affect all chillers at once. For air-cooled equipment, we need to watch out for coil fouling, corrosion, and blocked airflow, along with fan and motor health and proper staging controls. Cooling towers require attention to fan and gearbox condition, basin integrity, and maintaining the right water chemistry and hygiene according to regulations. Ensuring common mode proof involves verifying heat rejection capacity under design conditions, having independent power and control paths, and maintaining water and chemical supplies. It's also important to have safe manual modes and prepare chillers to handle any degradation in the thermal sink. Together, these elements ensure reliable and efficient heat rejection for the data center. This module focuses on the operations, maintenance, and readiness of data center MVAC systems, specifically advanced liquid cooling techniques. Modern liquid loops require careful attention to OEM-specific chemistry and cleanliness controls, so it's crucial not to apply limits from different coolants or server platforms. On the facility and CDU side, We manage components like plate heat exchangers, pumps with variable speed drives, filters, and strainers, monitoring pressure differentials closely. Expansion tanks, pressurization, relief valves, and air removal systems also play key roles in maintaining flow balance and bypass logic, supported by firmware backups and redundant controls. Moving to the technology loop, we check coolant identity, concentration, and pH or conductivity where needed, while inspecting quick disconnects, hoses, manifolds, and cold plates for leaks. Particle and fluid sampling help control contamination, and we rely on drip trays, leak detection cables, and automatic isolation to manage potential leaks. For immersion and state point liquid cooling, monitoring dielectric fluid condition and compatibility is vital, along with maintaining bath pumps, filters, and heat exchangers. Vapor and odor management, safe server handling, spill recovery, and proper disposal paths ensure operational safety. Throughout, understanding the roles of the CDU, PHE, coolant, quick disconnects, and leak detection systems is essential for effective maintenance and readiness. This module focuses on the critical aspects of operations, maintenance, and readiness for data center MVAC systems, with a special emphasis on water quality, leakage, and condensate management. One key practice is trending makeup water and chemistry, which serves as both a reliability tool and an early method for detecting leaks. For closed loops, it's important to sample at defined points regularly, monitor corrosion inhibitors and glycol levels where required, and check all strainers, separators, and expansion controls. Recording makeup water usage and investigating any unexplained increases helps catch potential issues early. Open systems require monitoring conductivity, makeup water, blowdown, and chemical stock while implementing scale, corrosion, and biological control through approved programs. The condition of basins and fills, along with water drift and balance, must also be tracked. Compliance with local water and discharge regulations is essential. When it comes to leak and condensate management, the use of leak cables, spot sensors, and zoning helps detect problems promptly. Components like drain pans, traps, float switches, and pumps must be regularly checked, and isolation valves should respond effectively. It's also crucial to preserve evidence of leaks before cleanup whenever it's safe to do so. By following these protocols, from sampling and chemistry to leak detection and condensate control, we ensure the system's integrity and performance. Remember, terms like COC for cycles of concentration, WLD for water leak detection, pH for acidity or alkalinity, and DP for differential pressure are key indicators used throughout this process. This module focuses on operations, maintenance, and readiness for data center MVAC systems, with a particular focus on computer room airflow and containment maintenance. One key point is that cooling capacity can be lost when bypass and recirculation occur after IT moves, adds, or changes. To avoid this, regular monthly walks are crucial to ensure blanking and rail seals are properly installed, cable openings are filled, floor tiles are correctly placed, and containment doors and panels close and seal properly. Sensors also need to be present, unobstructed, and correctly located. On a quarterly or annual basis, we check that cable management is not obstructing air, tile, and duct flows match rack demand. Uncontained or plenum systems are rebalanced after any material moves, adds, or changes, and computational fluid dynamics assumptions are validated when load geometry changes. To monitor effectiveness, we rely on evidence like rack inlet maps, hotspot trends, airflow and fan power from CRAH and fan wall units, containment differential pressure and leakage observations, as well as before and after photographs and commissioning checks. Remember, proper blanking, containment, cable management, tile placement, sensor positioning, and air balance all play integral roles in maintaining efficient cooling and system readiness. This slide covers refrigerant safety and recovery logistics, which are critical for operations, maintenance, and readiness in data center MVAC systems. Refrigerant work must always follow the approved safety analysis, relevant ASHRA 15 and AHJ regulations, refrigerant classification, and certified recovery practices. Detection and ventilation strategies are equally important. Detectors should be correctly located, alarm thresholds set properly, and ventilation and mitigation systems designed to match the specific refrigerant and machinery room setup. In case of an incident, the safe response protocol involves evacuating and securing the area, calling trained responders, preventing any ignition sources, and using the right personal protective equipment, or PP. Importantly, no one should enter an unsafe atmosphere without proper precautions. The recovery plan must include the right recovery machines and cylinders, careful inventory tracking, accurate labeling and weighing, leak-tight hoses, safe storage and transport, and compliance with jurisdictional record-keeping requirements. Lastly, drill frequency and the use of self-contained breathing apparatus, or SCBA, depend on project-specific risk levels and authority, having jurisdiction decisions. It's not a one-size-fits-all semi-annual mandate. And remember, training should rely on safe simulations, never by releasing refrigerant. This slide covers the working principle behind turning physical degradation into controlled maintenance for data center MVAC systems. The process begins by sensing key condition inputs like oil chemistry and vibration on the chiller compressor and triaxial vibration or motor current on pumps. Next, we establish a baseline and monitor trends to diagnose issues such as misalignment or fouling before they become critical. By risk ranking and planning accordingly, maintenance actions like inspecting tubes, aligning pumps, or cleaning heat exchangers are executed timely. Finally, functional proof ensures the system responds as expected, and baselines are updated to reflect restored performance. Early intervention is crucial. Acting before warning trends hit alarm limits helps prevent failures, supported by a decision rule that combines condition, consequence, redundancy, load, and lead time into a clear maintenance priority. This systematic approach ensures reliability and efficient operation of critical assets. Here we focus on the instrumentation and evidence architecture critical to the data center MVAC system. Every field point must demonstrate its operating state, performance, protection response, and restoration all aligned on one synchronized timeline. For example, monitoring parameters like temperature, relative humidity, flow, differential pressure, and valve position in IT load, CRAH, and CDU units is essential. Similarly, chilled water pumps are tracked through suction and discharge pressure, flow, power consumption, and vibration levels. Chillers require detailed monitoring of chilled water supply and return, flow, power, approach temperature, and any alarm conditions, while the heat-rejection system involves checking flow rates, temperatures, water levels, conductivity, and fan states. Ensuring data quality is fundamental. This means verifying range and units with declared engineering units and appropriate alarm limits, maintaining accuracy through proper sensor class and calibration records, and confirming timestamp consistency with common clocks and scan intervals. State mapping connects commands, feedback, permissives, alarms, and safe state logic to give a clear operational picture. Supporting systems like the Building Management System, trend historians, condition tools, CMMS work orders, and spares and competency records complete this architecture. Ultimately, we only accept evidence when the initiating event, operator action, equipment response, and restored state all share one perfectly time-aligned record, ensuring comprehensive and trustworthy operational insights. On this slide, we're focusing on the alarm philosophy for the data center MVAC system, which is key for operations, maintenance, and readiness. The most important concept here is that the condition, priority, response, and reset of an alarm all must align perfectly. An alarm without a clear owner and a tested response becomes just noise, which can distract and reduce effectiveness. Similarly, an override that never expires essentially hides changes in the plant configuration, leading to potential operational risks. To manage alarms effectively, we need to rationalize them by clearly defining elements like cause, deadband, delay, priority, suppression dependency, automatic and operator actions, escalation, and reset rules. This thorough definition helps ensure alarms are meaningful and actionable. Control overrides must be carefully regulated. They need proper authorization, a valid reason, and clear start and expiry times. Additionally, alarms affected by overrides should remain visible. There must be proper documentation during shift handovers and independent proof that normal operation sequences are restored after the override ends. Finally, to maintain and improve this system, we test by injecting safe, simulated signals or using specific test modes. We verify timestamps and notifications and review any alarm floods, missed alarms, repeats, and the overall usability for operators. This continuous cycle of testing and improvement ensures the alarm system remains reliable and effective. In this module, we focus on the operations scorecard for the data center MVAC system and how to interpret reliability, execution, and resource metrics together. First, it's crucial to declare boundaries, time intervals, data quality, and normalization before making any performance comparisons. For system availability, we measure uptime over total time, incorporating service-level event rules and defining planned exclusions to get accurate insights. Critical preventive maintenance compliance tracks critical tasks completed on time versus those due, with overdue work shown separately to avoid blending important data. Mean time to repair, or MTTR, is expressed as restoration hours over events, and it's important to separate diagnosis, repair, test, and approval delays to pinpoint where improvements are needed. Alarm quality is evaluated by the ratio of actionable alarms per operating hour, while tracking flood alarms, repeats, missed signals, and shelving duration. Cooling performance is monitored by cooling kilowatt hours per IT kilowatt hour, normalized for IT load, weather, temperature architecture, and operating mode. Similarly, water performance compares cooling water used to IT energy, declaring sources, makeup, blowdown, rain, reuse, and boundaries for clarity. To use the operations scorecard effectively, we look at trends by establishing baselines considering load and weather, annotating any changes. Diagnosis involves comparing capacity, alarms, energy, water, and reliability metrics. Acting requires assigning owners, setting thresholds, due dates, and verifying actions taken. Finally, closing the loop means proving recovery efforts succeeded without consuming system redundancy. This integrated approach helps ensure the MVAC system runs efficiently and reliably. Here we have a worked example that explains component availability and the meaning of MTTR, or mean time to repair. Availability is only meaningful when we clearly define the event boundaries and the protected service consistently. Starting with our inputs, we observe a total downtime of 18 hours over the year, with the system running for 8,760 hours in total. The mean time between failures, or MTBF, is 2,920 hours, while the MTTR is 6 hours. Using these values, we calculate availability A as MTBF divided by the sum of MTBF and MTTR. This comes out to 2,920 over 2,926, resulting in approximately 99.795% availability. It's important to note that this component availability figure does not automatically reflect system availability because factors like redundancy, common failure modes, detection delays, and operator recovery can affect the overall service impact. The calculation path includes defining the service, counting events, summing downtime, calculating MTBF and MTTR, computing availability, and validating the scope. For accurate and transparent reporting, preserve raw event data and assumptions, and always use the service level boundary for business reporting. This approach ensures you have a reliable understanding of component availability and its relevance to operational readiness. Here, we examine a worked example focusing on criticality-weighted preventive maintenance compliance and spare parts coverage. A high overall compliance percentage can be misleading if critical tasks protecting the IT load are overdue. For instance, while the raw KPI shows 92% compliance, once we apply a weighting of 5:1 between critical and standard tasks, the weighted KPI drops to 86.7%. This tells us that 4 critical tasks are overdue, which is a significant concern despite the seemingly high raw score. On the spares side, we see 90% coverage, but it's crucial to consider the consequence and lead time of missing items, like a missing PLC I/O module, which could have a greater impact than several low-risk parts. The recommended actions include protecting the affected failure domain, defining vendor or loan stock responses, scheduling critical PM tasks promptly, and tracking these to verified closure. In summary, this example highlights the importance of classifying tasks by criticality, applying appropriate weights, identifying gaps, and escalating issues to ensure reliability and minimize risk in data center operations. In this module, we'll focus on the critical spares strategy for the data center MVAC system, emphasizing that the goal is recoverability, not just having the largest warehouse. We base our strategy on risk by considering factors such as failure consequences, installed quantity, MTBF or failure history, and detectability. We also evaluate vendor stock availability, logistics, repair lead times, and whether the system can operate safely without the part. Configuration control is essential, ensuring we have the exact model, compatible firmware, and approved substitutes. We need to manage shelf life, preservation, and storage environments carefully, including battery and capacitor rotation with periodic testing. All spares should be tracked with barcodes, locations, and issue and return histories. Recovery readiness involves testing or inspecting high-risk spares when possible. It also means having the necessary tools, licenses, cables, and configuration backups ready. Defining escalation paths with vendors and loan stocks is critical, along with replenishing stock immediately after use. Key factors we continuously consider include criticality, lead time, compatibility, shelf life, storage conditions, and recovery testing. This thorough approach ensures that when failure occurs, recovery is swift and efficient, minimizing downtime and maintaining operational integrity. On this slide, we're focusing on maintenance contracts and response SLAs for the data center MVAC system. It's crucial to translate vendor capabilities into clear, measurable obligations around coverage, escalation, and proof of work. Starting with the scope, this includes the asset list, the tasks and their frequency, parts and consumables, warranties, software and firmware updates, calibration, and any excluded work. When it comes to response, it covers everything from callbacks and remote expert support to site attendance and recovery targets, including 24/7 coverage where necessary and defined escalation contacts. Execution quality is another key area. We ensure qualified personnel follow approved methods of procedure, adhere to safety practices including lockout/tagout, and use proper tools, parts, and test equipment. Completing service reports and providing return-to-service proof are also mandatory. On the commercial and KPI side, contracts specify rates, travel, after-hours charges, reporting requirements, downtime definitions, and performance metrics like PUE or efficiency. Penalties or bonuses may be included to reinforce performance goals. This comprehensive approach ensures that maintenance and readiness align tightly with operational requirements and expectations. In this module, we're focusing on redundancy, failure domains, and maintainability within data center MVAC systems. Capacity redundancy is truly credible only when distribution, power, controls, and shared dependencies all remain independent during maintenance or work. Let's break that down. First, capacity involves elements like duty and standby units, live load forecasting, derating, the next failure deficit, and load shed thresholds. For distribution, it's critical to have separate headers and branches, the smallest isolatable segments, remote path duties, and proper drain and vent behavior. When it comes to power and controls, independence is key. That means independent sources, starters or variable speed drives, controllers, networks, sensors, configuration, and restart sequences all must be separate to prevent cascading failures. We must also consider common modes of failure which can arise from shared chemistry, heat sinks, make up water, sensor bias, network access, temporary work, and human error. All factors that can undermine true redundancy. To maintain operational integrity, there's a clearly defined maintenance release gate process. Declare the load, map the domain, prove the standby system, isolate the segment, conduct load tests, and then restore the system. Remember this crucial hold point. Do not confuse spare capacity with a fully independent alternate service path. This distinction ensures that redundancy offers real protection and reliability during maintenance activities. In this module, we focus on operations, maintenance, and readiness specifically for the data center MVAC system. A key aspect here is the risk-based change management process and the role of the Change Review Board, or CRB. No operational asset change moves forward without a documented scope, risk analysis, approvals, clear communication, and a rollback or restoration plan. We categorize changes into 3 types. First, scheduled or low-risk changes are routine and do not reduce normal system function. These are logged and carried out by qualified personnel. Next, planned or medium-risk changes may affect system redundancy or settings and require peer review, detailed methods of procedure, or MOP, and coordination among stakeholders. Lastly, critical or emergency changes involve significant safety or service risks and call for immediate incident authority activation using an emergency change process. The CRB evaluates each change request by reviewing several factors: system impact, risk score, the MOP, the point of no return, regression plans, timing, approvals, and notifications. This thorough review ensures all changes maintain system integrity and operational readiness at every step. This slide covers the anatomy of a maintenance or method of procedure, or MOP, which is essential for turning a risky intervention into a series of controlled and manageable steps. Each step in the MOP clearly defines the action to be taken, the expected response, how to verify success, when to abort if something goes wrong, who has the authority, and what evidence must be recorded. The authorization phase ensures that the approved scope and risks are understood. The current plant state and live load are known, and communication roles and the critical point of no return are established. Then, during controlled steps, we focus on the specific actions and the expected plant responses, along with independent verification and hold points. It's crucial to have abort conditions and rollback actions ready, with evidence documented every step of the way. Finally, the return to service phase involves removing any temporary states or lockout/tagout procedures, confirming all commands, feedback, safeties, and alarms are functioning, conducting load tests, monitoring trend stability, and obtaining independent sign-offs. These carefully structured phases help maintain operational safety and reliability throughout the MOP process. As we move from commissioning to operations and maintenance, it's critical to prove the asset before taking on the maintenance responsibilities. This means the design, installation, and startup evidence become the foundation for all future maintenance and troubleshooting activities. Starting with the design phase, the approved duty and operating envelope must be clearly defined. We need to understand the OEM's maintenance strategy and access requirements, be familiar with the system controls, alarms, and failure modes, and ensure any factory performance issues or defects have been resolved through the factory acceptance test. During installation, proper tagging, orientation, and service clearances are essential. Isolation points, drains, vents, and lifting provisions must be carefully implemented. Cleanliness is vital, along with thorough pressure and leak tests. Sensors, cabling, and network terminations need to be properly installed and verified. For startup, or the site acceptance test, pre-start checks, equipment rotation, safety functions, and point-to-point connections are confirmed. Initial tuning and set point registers are established, alarm routing and failover systems are tested, and baseline measurements like vibration, flow, power, and performance are recorded. These three phases, design, installation, and startup, form the baseline that supports ongoing operations and maintenance. Once the equipment maintenance plan is loaded, spares are verified, and operations formally accept the system, we have a solid platform for reliable and efficient data center MVAC system management. This slide covers the operations readiness test program for our data center MVAC system, focusing on routine proof, failure drills, and restoration. Key activities happen on different schedules to ensure continuous reliability. Daily tasks include rounds, leak checks, alarms, and trend reviews. Monthly, we rotate standby equipment and test automatic sequences. Quarterly, we conduct MOP and EOP drills and verify communication protocols. Every 6 months, we swap duties, calibrate equipment, and review water quality. Annually, representative high-level tests and system restoration proofs are performed. The program involves monitoring synchronized data from the BMS and CPOS, tracking command status, trends, and alarms across key equipment like IT load banks, CRAH and CDU heat capture, chilled water pumps, chillers, condenser pumps, and cooling towers. We run specific failure drills, such as simulating chiller or pump trips, cooling tower fan loss, BMS communication loss, water quality excursions, and leak detection. For each, we inject a fault and expect a defined response to maintain system stability and safety. Acceptance criteria are strict. Response times must meet targets, temperature excursions stay within limits, capacity must meet requirements, and alarms and operator actions need to be accurate and timely, all documented through event logs, trend reports, and operator records. Finally, the restoration gate confirms that the system returns to normal lineup, overrides are closed, standby equipment is available, and all evidence is signed and time-aligned. Remember, a drill is only complete once the system is fully restored and the evidence package is closed. This thorough approach ensures our data center cooling system remains reliable and ready at all times. On this slide, we focus on the acceptance criteria and evidence pack critical for operations, maintenance, and readiness of the data center MVAC system. Before any work begins, pass or fail criteria must be clearly approved and directly linked to the design intent, plant state, and assigned accountability. For each acceptance criterion, there is a required proof and a designated accountable owner to ensure responsibility is clear. For example, procedures must be approved with signed methods of procedure, risk reviews, permits, hold points, and rollback plans, overseen by the operations authority. The training owner ensures people involved are competent through proper briefing, role assignment, authorization, and observed performance. Maintenance leads verify critical spares are available and ready, considering factors like stock levels, shelf life, compatibility, and recovery time. The duty engineer confirms redundancy is protected by validating live load, standby proof, failure domain maps, and isolation procedures. Commissioning leads proof performance with time-aligned trends, calibrated measurements, alarms, and representative load tests. Finally, the incident authority confirms restoration completeness by verifying normal lineup, closed overrides, cleared alarms, standby availability, and proper sign-off. This structured approach flows through 4 key phases. Ready, which ensures scope, people, and capacity. Execute, focusing on controlled work within watch limits. Prove, involving functional testing under load. And close, which finalizes restoration and provides indexed evidence. Together, these steps maintain the highest standards for system reliability and operational excellence. Here we focus on the failure mode register, which is a crucial tool for managing data center MVAC systems. The idea is to systematically rank failures based on several criteria: service consequence, detectability, automatic response, alternate path availability, and restoration complexity. This helps us prioritize and address the most impactful issues first. The register itself includes detailed fields covering the failure event, its initiator, and the protected service affected. It also tracks detection methods, alarms, and how the system automatically responds. Additionally, it notes alternate paths for service, isolation techniques, and restoration methods. Risk ranking plays a key role by evaluating factors like life safety implications, detectability, potential common mode failures, and residual capacity. It also considers the time, spare parts availability, required skills, and overall complexity needed to recover from a failure. To maintain readiness, established actions include approved emergency operating procedures, decision authority, required spares, tools, test methods, and relevant training scenarios. Responsibilities are clearly assigned, along with due dates, acceptance evidence, and review triggers to keep everything on track. This whole process, from identification through detection, response, containment, restoration, and finally learning, forms a comprehensive approach to ensuring system reliability and resilience. Some important acronyms here include FMEA, which stands for Failure Modes and Effects Analysis, EOP for Emergency Operating Procedure, BMS for Building Management System, and CPOS for Cooling Plant Optimization System. This slide outlines the troubleshooting workflow for the data center MVAC system, emphasizing a structured and safe approach. First, we stabilize the service by declaring authority, protecting life and IT load, and using approved emergency operating procedures. Then, we verify the system state by checking modes, permissives, overrides, and comparing command signals to actual feedback, ensuring the equipment lineup is correct. Next, we validate sensing by cross-checking local gauges, confirming calibration in units, and comparing redundant points to ensure accurate readings. After that, we isolate the domain by focusing on capacity, distribution, power, controls, network, and any shared water or heat sinks. The fifth step is to correct the issue using an approved repair or adjustment, making one controlled change at a time while recording the state before and after. Finally, we prove recovery with a representative load test, confirming alarms and standby systems are available and documenting evidence of restoration. Throughout this process, there is a crucial hold point. Halt work if there is any uncertainty about safety, capacity, sensing validity, authorization, isolation, or restoration evidence. This disciplined workflow helps ensure both operational stability and safety. In this module, we focus on the standard operating cycle for data center MVAC systems, covering operations, maintenance, and readiness. First, normal operation is defined not as the absence of alarms, but as a continuously declared, monitored, and auditable state. This means we have to actively declare what normal looks like by considering live IT and MVAC load, forecasts, duty and standby lineup, TS states, and approved operational envelopes with residual capacity. Next, during operation and monitoring, it's essential to strictly follow startup, shutdown, and sequencing standard operating procedures. We must continuously review trends, alarms, patrol findings, and any overrides, escalating any degraded or ambiguous conditions. When restoring and recording, the focus shifts to moving any abnormal responses into the approved emergency operating procedures. We then prove equipment performance under load, return systems to automatic operation, and ensure all actions are properly closed in the computerized maintenance management system, especially during shift handovers. Throughout this cycle, steps like declaring, verifying, operating, monitoring, restoring, and recording are crucial for maintaining system readiness and reliability. In an emergency operating response for a data center MVAC system, life safety and thermal stabilization come first. It's critical to preserve evidence and restore systems deliberately. The first step is to declare incident authority by identifying the event, its location, and the affected service. Then, assign a decision maker and response roles while starting a time-stamped event log. Next, stabilize thermal conditions by verifying the actual plant state and sensor readings, activating any available standby or thermal energy storage paths, and protecting IT inlet and liquid supply limits. Always use the approved emergency operating procedure, following pre-planned steps and escalation protocols, documenting every deviation and decision, and never defeating local safety measures. Finally, communicate clearly about load, margin, risk, and provide updates. After repairs, test the service under load and complete a two-person return to normal review. This structured approach ensures a safe and effective response. This module focuses on dealing with a sudden chiller trip when the IT load is high, a critical situation in data center MVAC systems. First, it's important to respond to the overall service impact, not just the failed chiller. Immediately, we need to stabilize the system by confirming the trip and chilled water supply trends, starting any available standby units per the sequence of operations, checking pumps and valves, and declaring an incident if the cooling margin is at risk. Next, protecting the load is crucial. This involves using thermal energy storage or alternate cooling paths, tightening watch limits, halting non-essential maintenance, and coordinating rack or load actions if certain thresholds are met. Then comes diagnosis, where we validate sensors and safeties, inspect power and flow, check the heat sink, refrigerant, and controls, and preserve the trip data before resetting any equipment. Finally, restoration requires repairing the issue, proving the system can handle the load safely, returning to normal sequences, replenishing thermal storage, monitoring stable operation, and completing a thorough root cause analysis. This structured approach helps maintain data center reliability even under unexpected chiller failures. This module focuses on handling a chilled water leak or flooding event in a data center MVAC system. The first priority is to protect people and energized equipment, contain the leak, maintain an alternate cooling path, and preserve evidence. The process starts with detecting and classifying the leak by locating the water leak detection zone, verifying it from a safe route, and identifying the exact pipe, valve, or coil source, especially if it's near energized equipment. Next, we contain the leak by stopping or closing only approved devices to isolate the smallest segment. Barriers or wet vacuums are deployed, and coordination with electrical safety and drainage teams is essential. Maintaining cooling is critical during this event, so you need to confirm the residual duty, ensure the alternate path and air or liquid distribution are functioning, and continuously monitor IT inlet and rack temperatures. Finally, during recovery, repairs involve pressure and leak testing, drying and cleaning the affected areas, inspecting insulation and sensors, refilling, venting, and testing with water before restoring the system under load, and completing a root cause analysis. These steps are key to managing the situation safely and effectively. In this module, we're focusing on operations, maintenance, and readiness specifically for the data center MVAC system. The scenario we're addressing is a failure in the CPOS or BMS network or controller. Importantly, even when the network or controller fails, local equipment safeties remain authoritative/emphasis, and any manual operation is controlled carefully, time-limited, and fully visible to ensure safety. First, it's crucial to confirm the scope of the issue. We need to distinguish between different types of failures, such as display or server loss, network partitions, controller failure, I/O failure, or bad sensor data, and always verify status at the local panels. Next, stabilizing the system locally comes into play. This involves using validated fallback procedures or approved manual sequences, maintaining fixed safe set points, and importantly, avoiding conflicting manual and automatic commands. When it's time to recover control, the focus shifts to restoring the redundant server, network, or controller. We must verify key elements like configuration, time synchronization, point quality, command and feedback channels, as well as alarm routing to ensure everything is functioning correctly. Finally, when returning to automatic control, it's essential to peer check every override, transfer control one system at a time, prove lead and lag functions, failover and restart capabilities, and monitor trends for any hunting or stale commands. Throughout this process, understanding that CPOS stands for Cooling Plant Optimization System, BMS means Building Management System, PLC refers to Programmable Logic Controller, and I/O stands for Input-Output helps clarify the technical terms involved. Here we have a worked example focusing on TES, or thermal energy storage, specifically examining the thermal bridge during blackout recovery. It's important to note that TES duration is a measured system property, and simply having stored volume does not guarantee the system can maintain ride-through on its own. Starting with the key parameters. The TES volume is 60 cubic meters, the temperature difference, or delta T, is 10 Kelvin, and the usable factor is 0.85. When we calculate thermal energy, we multiply these factors together using the formula E equals 1.163 kilowatt-hours per cubic meter per Kelvin times volume times delta T times the usable factor, resulting in 593 kilowatt-hours thermal. Next, to find the ride-through duration, we divide that stored energy by the load, which is 5.20 megawatts thermal, then multiply by 60 to convert hours to minutes. This gives us a result of 6.84 minutes of ride-through capability, compared to the theoretical maximum of 8.05 minutes. However, the actual performance depends on several system factors: the availability of TES pump and control power, the correct operation of charge and discharge valves, usable stratification and proper sensor function, and the distribution through CRAH, FWU, or CDU systems. Based on this, the key takeaway is to use the lower, field-validated duration when defining the emergency operating procedures, and to initiate upstream recovery before the thermal bridge is fully consumed. Also, fuel autonomy and response time targets vary by site, business continuity plan, and authority having jurisdiction. So presenting fixed values like 12 or 24 hours as a universal mandate isn't appropriate. This slide covers how to handle a refrigerant leak or machinery room alarm in a data center MVAC system. First and foremost, do not enter or isolate equipment until the atmosphere is confirmed safe, the refrigerant hazard is assessed, and an approved response plan is in place. Our priority is to protect people. This means acknowledging the alarm remotely, evacuating or securing the area, contacting trained responders, accounting for all personnel, and following proper alarm and ventilation procedures. Next, protecting the plant involves not resetting or bypassing detectors, assessing the availability of adjacent cooling, and only starting alternate cooling from a safe location using an approved sequence. Controlling the release requires specialists to identify the source, isolate it if safe, recover refrigerant using the correct equipment, and continuously monitor the atmosphere as per the response plan. Finally, restoration includes performing leak and pressure tests, making repairs, vacuuming and recharging according to the manufacturer's guidelines, proving detection and ventilation systems are functioning, load testing equipment, reconciling the refrigerant log, and completing a thorough event review. Remember, the use of proper personal protective equipment, such as SCBA, and following jurisdictional authority rules is critical throughout this process. After a significant seismic event, it's critical to conduct a thorough post-seismic audit of the MVAC system before restarting any rotating or pressurized equipment. First, we declare the situation by activating the site's seismic emergency operating procedure, restricting access, and confirming personnel safety. Next, perform a detailed visual survey for leaks, unusual odors, alarms, and check pipe and riser joints, as well as any equipment displacement. Then, inspect all supports including spring isolator positions, anchors, braces, guides, and flexible connectors. Assess the fluid paths by checking headers, valves, plate heat exchangers, thermal energy storage units, refrigerant lines, drains, and containment systems. Follow this with a controls and power review, verifying sensors, control panels, cables, emergency power status, interlocks, and safety systems. Finally, proceed with a controlled restart, bringing up one system train at a time while closely observing for vibration or leaks, conducting load tests, and obtaining sign-off. Remember the key hold point. Do not restart if there is structural damage, hidden leaks, abnormal isolator deflection, electrical hazards, or uncertain pipe stress. This structured approach ensures both safety and system readiness after an earthquake. On this slide, we focus on the event record, root cause, and lessons learned process for the data center MVAC system. It's important to understand that an event is not considered closed simply when cooling is restored. Instead, closure only happens after the cause of the event, the recovery steps, and the prevention actions have all been verified. The process is broken down into 6 key steps. First, capture everything, including the time, event details, location, and both indoor and outdoor conditions. Don't forget to note the alarm status and initial state. Second, decisions are reviewed. This involves considering all options, explaining why certain actions were selected or rejected, and noting any deviations from the emergency operating procedures. Third is establishing a timeline, documenting all actions taken, identifying who was responsible, recording equipment responses, and tracking communications throughout the event. Fourth, validation takes place, where repair evidence is gathered, functional and load tests are conducted, and a 2-person review is completed for accuracy. Fifth, analyze the event by identifying direct, contributing, and latent causes, including human, technical, and process factors. Sixth and finally, improve by updating procedures such as the emergency operating procedures and maintenance plans, replenishing spare parts, and tracking actions to closure. At the very end, the closeout step involves communicating the full report to operations and providing an appropriate summary to management and all affected users. This thorough approach ensures continuous improvement and readiness. This module focuses on operations, maintenance, and readiness for data center MVAC systems, emphasizing the importance of emergency drills and a competency program. Our goal is to train personnel in normal operations, maintenance, and failure recovery behaviors without causing any uncontrolled risk to the live plant. The training ladder is designed to build skills progressively, starting from classroom instruction, moving to schematic walkdowns, simulator or tabletop exercises, supervised field tasks, observed emergency drills, and finally periodic reauthorization to maintain proficiency. Safe fault injection is a critical aspect, where we use test modes, digital twins, spare controllers, or tightly controlled signals to simulate faults, always avoiding real pipe ruptures or compromising local safety systems during training. The scenario portfolio covers a range of incidents including chiller trips, flow loss, sensor bias, CPOS loss, leaks or floods, refrigerant alarms, smoke ingress, blackouts with thermal energy storage impacts, and seismic events. Assessment focuses on key areas like the time taken to recognize and stabilize issues, adherence to procedures, communication effectiveness, quality of evidence gathered, restoration efforts, and closing lessons learned with actions. This comprehensive approach ensures readiness while maintaining operational safety and reliability. This slide outlines the 90-day handover and operational readiness plan for the data center MVAC system, part of Advanced Training Module 18. The asset is considered ready only when 4 critical elements are fully documented and exercised: technical data, procedures, spares, and competency. During the first 30 days, our focus is to establish the baseline by freezing as-builts, sequences of operation, set points, and the asset register. We also load maintenance tasks and warranty dates into the computerized system and capture important performance baselines such as vibration, flow, power, and thermal data. From days 31 to 60, we move to proving the system readiness. This involves completing operator and OEM training, conducting walkdowns, validating all procedures and the alarm matrix, and ensuring spares, tools, and vendor support are in place. Finally, in the last 30 days, from day 61 to 90, we exercise the system readiness through maintenance procedures, integrated emergency drills, and by closing any defects. The readiness scorecard is then issued to confirm the asset meets all requirements before sign-off. This structured approach ensures that the system is fully prepared and safe for operation, minimizing risks and enhancing reliability. In this practical lab, our goal is to build a critical maintenance plan for one live MVAC asset, focusing on authorizing a safe maintenance window while maintaining the required thermal service. The process starts by analyzing the system to freeze the live load and operating envelope, then mapping the failure domain along with alternate paths. Next, we plan by developing an EMP task, method of procedure, and hold points, ensuring all tools, spares, personnel, and evidence are clearly defined. Execution involves following this plan precisely. The output includes a marked-up service path, residual capacity calculation, a method of procedure with an acceptance checklist, and a CMMS work order complete with an evidence index. To pass, an independent reviewer must be able to execute, halt, roll back, test, and restore the plant without relying on undocumented knowledge. This structured approach guarantees safety and reliability throughout maintenance activities. In this module, we focus on the data center MVAC system with an advanced training session designed to sharpen practical skills. The key objective here is to calculate essential metrics like availability, critical preventive maintenance compliance, mean time to repair, and spare risk indicators using a sample event log. We'll start by defining clear service and event boundaries, then calculate MTBF, MTTR, and overall system availability. It's important to separate out critical overdue tasks, as they can significantly impact system reliability, and rank missing spares based on their potential consequences and lead times. To ensure accuracy, we'll apply strict controls by checking data quality, verifying common timestamps, accounting for planned exclusions, and using classification rules with management-approved weightings. Finally, every KPI we produce can be traced back to actual operational data, including alarms, work orders, restoration tests, asset criticality, and spare parts records. This thorough approach ensures the KPIs truly reflect service risk rather than obscuring it in simple blended percentages. This module covers the critical operations, maintenance, and readiness aspects for the data center MVAC system during an emergency scenario. Our practical exercise focuses on managing a chiller trip combined with a misleading temperature sensor. The scenario presents a high IT load situation where the duty chiller trips. One room sensor reads 4 Kelvin higher than actual, and the standby chiller start is delayed. The response strategy begins by declaring authority and validating sensor readings to avoid false actions. Then we start an alternate cooling path or thermal energy storage while protecting rack inlet temperature limits. If the IT load approaches its ceiling, we escalate the response to prevent damage. However, there are residual risks to consider, such as the possibility of a second failure while the system is already degraded, incorrect actions triggered by the biased sensor, depletion of the thermal energy storage, or failure to restore manual override controls. We document all evidence meticulously, including the timeline, sensor comparisons, chilled water supply and flow trends, operator decisions, standby tests, and restoration sign-offs. These help us learn valuable lessons to improve future emergency readiness and response. In this module, we focus on operations, maintenance, and readiness of the data center MVAC system, with an emphasis on advanced training. The key to competency here is not just recalling information, but demonstrating solid engineering judgment, strict procedural discipline, and producing quality evidence. You'll need to be able to explain the entire heat removal path, understand the ownership interfaces, identify common failure modes, and know the safe operating envelope. Calculations are critical too, including residual capacity, availability and mean time to repair, PM compliance, TES duration, flow and temperature performance, and risk prioritization. You will also practice diagnosing issues by separating failures across sensing, controls, distribution, power, water and refrigerant, and mechanical systems, all without compromising safety measures. Beyond diagnosis, you must operate, prove, escalate, restore, communicate, and continuously learn, all following established procedures like SOPs, MOPs, EOPs, and MOCs. This comprehensive approach ensures effective and safe management of the MVAC system. This module focuses on operations, maintenance, and readiness for data center MVAC systems. One of the most critical points is to always use licensed standards, approved project documents, and current OEM data while verifying additions before live adoption. We rely heavily on primary reference families such as BICSI 009-2019, with a gap check to ANSI/BICSI 009-2024, the ANSI/TIA 942C infrastructure standard, the Uptime Institute Tier Standard for Operational Sustainability, and OSHRI TC 9.9 for thermal and liquid cooling guidance. Safety and performance standards include ANSI/ASHRAE Standard 15 to 2024 and 90.4 to 2025, alongside ISO standards for power and water usage effectiveness. It's important to maintain comprehensive project evidence like OPR, BOD, as-builts, OEM manuals, warranty info, and calibration histories. Always confirm that you are working with the current editions as of August 2026, especially for compliance decisions. The logical next step is to issue a site-specific O&M gap assessment and create a prioritized readiness action register to ensure operational excellence. As we conclude Module 18 on operations, maintenance, and readiness, let's focus on the closing principles that ensure the reliability of data center MVAC systems. Readiness is a controlled operating condition that depends on more than just design. It requires that people, procedures, maintenance, and evidence all stay perfectly aligned. Protecting the service means prioritizing life safety first. Always understanding the live load, the operating envelope, alternate paths, and anticipating the next credible failure before any intervention. Controlling the work involves using approved procedures like SOPs, MOPs, and EOPs, ensuring competent personnel, implementing lockout/tagout, peer checks, hold points, time-limited overrides, and having clear stop work authority. Finally, to prove and improve, we need to test under representative load, restore normal and standby lineups, document evidence thoroughly, learn from events, and continuously update the program. This structured approach maintains system resilience and service availability at the highest level.